An aquatic plant requires 4 basic ingredients: sunlight, water, nutrients, and CO2 to output energy. It's an immutable equation. If you drop the sunlight to a fraction of a percent, the energy output crashes and the biological process halts. Plants simply don't grow in the dark. But in the mid-20th century, early scuba divers in the Mediterranean descended deep into the ocean's twilight zone and found something completely anomalous. Their new deep-water breathing technology allowed them to physically cross a border where those standard surface rules of biology no longer seem to apply. This depth chart maps out exactly what they swam into: the Mesophotic zone. Spanning 30 to 150 meters below the surface, the light here drops off exponentially. By the bottom of this zone, only 0.1% of surface sunlight remains. Yet out of that darkness emerged a dense underwater forest of giant kelp, with individual stalks growing over twice the size of a giraffe. Oddly enough, the specimens surviving in this extreme darkness actually grow significantly larger than their counterparts living in shallow, sunlit waters. Look at this balance scale, because the math doesn't work. Even with massive leaves capturing stray photons, they don't harvest enough energy to balance out the immense cost of their own growth and respiration. How does an organism powered by light build massive underwater skyscrapers in near-total darkness? Survival here requires a total shift away from increasing energy production toward extreme energy conservation. In shallow aquatic cells, massive energy is spent converting complex bicarbonate molecules into usable CO2 for photosynthesis. But the deep Mesophotic zone is naturally rich with ready-to-use CO2. Through passive diffusion, deep kelp absorbs this free CO2, completely bypassing the energy-burning chemical conversion. By exploiting this environmental loophole, the deep-water kelp gets a massive chunk of its diet for free, balancing its energy budget against the darkness. That's their biggest biological expense cut, but it's not the only one. The kelp also avoids the high cost of producing molecular sunscreen. Plants near the surface have to divert precious energy to defend themselves from constant solar radiation. Safely hidden in the dark, Mesophotic kelp takes all the energy that would have been spent on protection and routes it directly into growth. The third and most extreme adaptation is how they handle the pitch-black winter months. When the little light they have vanishes, the kelp doesn't fight it. It suppresses its own respiration, hibernating and surviving exclusively on the carbon reserves it hoarded over the summer. By stripping away biological luxuries like solar defense mechanisms and winter growth cycles, the Mesophotic kelp achieves a state of extreme thriftiness. It thrives in a barren zone by refusing to waste a single drop of energy. The extreme depth provides another advantage. Because the Mesophotic zone is isolated from the sun, its water temperature is stable year-round. That unique stability turns these forests into vital climate refuges. When surface waters heat up, shallower marine species fleeing surface heat waves migrate down into the protective, cool canopy of the deep kelp. The kelp itself also acts as a carbon sink. As pieces of the plant break off, that detritus drifts down to the ocean floor, continuing to pull down atmospheric CO2 and lock it away. We still don't know the exact impact these plants have on the global carbon cycle, largely because they are entirely invisible to mapping satellites. Discovering them requires researchers to drop specialized, remotely operated robotic vehicles into the deep ocean, like the ones recently deployed to map a new mesophotic forest off the coast of the Galapagos Islands. It leaves us to wonder how much of the seafloor they actually cover. Massive forests that we haven't even found yet, hiding in the dark, quietly stabilizing the deep ocean environment.